now we're going to go into the first talk of the evening. Big round of applause, please, for Bart Smith.
Good evening. This is a talk about something which I'm not an expert on, but something which I wanted to learn more about. It's about how the kernel works in relation to container and to container security. But before we start, just a little bit about me. It's not about how you secure Docker. For that, you can watch the video of last month by Adrian. I can highly recommend it. It has many views. The slide deck will be available later, and I put all the on the bottom. I put all the URLs, so you will be able to find them. So a little bit. So we talk about entropy. So what is security? And relation between security and entropy, and then I will take you in a sort of a voyage at what is happening in the kernel space, and what all kind of initiatives there are in the space of the kernel and Docker. About me, I started 23 years ago with Windows NT Kernel Developers Conference in London. I traveled to London, had to sleep. I didn't have the money to rent a hotel room, so I slept with someone else in a hotel room, and she kicked me out of the bed because so I slept on the floor. It was an interesting experience. The Device Driver Conference in '92, I think it was. So I got even floppy disks with the Windows NT on it. So that was a long time ago. Then I trained people for many years. I'm 20 years Microsoft certified trainer, and I design systems for enterprise customers mainly, do troubleshooting. And 4 months ago, I decided to quit Microsoft and reboot myself and make the jump to web scale. So I've been going to many meetups, and one of the things which really intrigued me, because I'm also interested in the security, is how does security work with the kernel, with Docker, where are we going? So that's my presentation. So just give a brief background on security. If we look at the fortress, how do you protect the fortress? You can have many doors or few doors. Few doors, you win. You can have easy doors to block, or you can have complex doors to block. You can have complex interfaces of computers, you can have complex interstate, and those are more difficult to defend. And then the third way you can defend the fortress is with a multi-layer tactic. These are the three options. Of course, you can mix and match them, and if you have many layers, it becomes more complex, so there's always a trade-off. I'd like to show you these pictures of Peter Sewell. He's a professor in Cambridge. He gave a very nice presentation at the last CCC conference. And what you see here is, he depicts a computer hardware, TCP stack, the file system, the C compiler, JavaScript, TLS, and then the browser, and then on top of that, the software what we run to go to our bank. So you get the picture. Entropy. A lot of entry points, many ways things can go wrong. So in Cambridge they do some really nice research. I'll come back to them later. We all know the SPI stack, SaaS, PaaS, infrastructure as a service. Let's take a look at how we look at that from security perspective and from developer's perspective. First of all, we have infrastructure as a service. Always uses hardware virtualization. What is hardware virtualization? Probably most of you know that. You have a hypervisor which virtualizes hardware. So to the operating system on top of that, it looks like you have another piece of hardware. On top of that, we run our applications. What's the problem with this? Performance. You have to go through that virtualization layer, and that takes time, it takes performance. And not only that, you cannot easily expand the memory. I know people who install the VMware and they always give it a fixed amount of memory. They don't use the memory bloating, but that means you have to buy a lot of hardware, a lot of RAM. Recently we had a meetup with some people of OpenStack, and there was someone from the Ministry of Internal Affairs, and they usually buy servers with 786 megs of RAM, gigs of RAM. And then 10K RPM disks. So you pay easily 20,000 euro for a machine like that, or even more. That's completely opposite to web scale, at least from my perspective. They don't buy small machines, which if they fail, you just throw them away. No, you buy big machines and you scale up. But there's a big advantage of virtualization. It's easy to defend. There are some ways to get out of a VM, but usually Gartner and all the others, they think VMs are safe. So banks in Holland, they run on one platform. If they run on the x86 platform, that is the VMware. There's one advantage, and that is you can run and install anything you want on that operating system. So for the developer, it's nice. Some examples: Amazon. Anyone knows how many servers Amazon has compared to the next competitor?
10x.
Sorry?
10x? 10 times more?
How much do they have compared to all others?
More.
10x.
5 times. 5 times more servers than the complete all of the others competitors. Amazon is big. Microsoft is coming in. They have twice as much as the next 13 competitors. And then there's the rest. I put that joint for a specific reason. We'll see it later. Why? Okay. Then there's PaaS. PaaS is you have a set of services which are fixed underneath some operating system, and on top you can run your own application. Google is a good example of that, but the problem is you cannot expand the number of services. You're fixed with what Google has to offer. You're locked in. If you have a new database server you want to use or something, you're screwed. You cannot change to the new database server. Some examples. Then there comes containers. And Jerome explained it in a session he gave months ago, very nicely. A container is nothing else than a normal process, but it only has a few extra labels. So the protection is the same protection you get from a normal interprocess on a normal operating system. But you also get the speed of normal interprocess communication. So you do get a processor switch, context switch, but you don't have to switch through a complete virtualization layer. A container, from the perspective of the operating system, you see an application. From the perspective of an application, you see a virtual machine. So it is a virtual operating system, it's not a virtual machine. You don't see virtual hardware. You see the same hardware, which is on the underlying layer. But it's fast. You get all the speed of normal interprocess communication, and you can expand it. If it needs more memory, it just grabs the memory, and of course you can limit it, but it can easily expand memory just like the normal process. If your browser runs more tabs, it can expand, and similar with containers. But how about security? That's the talk of tonight. For the last one, I don't want to go into much depth. Another of those asks. So, if we just look at the pass, developers don't like it because they cannot expand the services. They have a fixed limit of services, database, one web server, etc. Containers are nice because you can install what you want and it performs really nice. And infrastructure or virtualization is not nice because you don't get the performance. And then the question for tonight, what do we do with security? How about security? Are containers secure or aren't they secure? I'm not going through this list. This is from the website for Wikipedia, list of all the container solutions available. But I'm just going to pick a few and look what the capabilities are and compare them and see where things are going. Docker. Docker, before 0.19, was just LXC, so Linux containers, as invented like, I think 2004, I think it started, with an interface, with a Go interface, with a Go, written in Go, interface into LXC. Then, in last year, 0.9, they updated and they said, we will include the container functionality in Docker. That's for versioning, makes it easier to maintain. You don't depend on minor changes in the next version of LXC. So what did they do? They called it libcontainer. But it's still possible to run LXC. You need a special option, minus LXC, minus ELXC. So then you get plain LXC. It has, you have to do some more tricks than only that, but eventually you get it work. And then, 2 weeks ago, Docker announced at the Docker conference the run C. So when you have here setting up LXC Docker version 1.xx when you do an installation of Docker, now that eventually will become run C. And run C will have more than only LXC, but from the security perspective, it's quite similar. And it's supported by many more vendors. CoreOS. Not. One vendor not. Who knows which vendor? Who wasn't on the list of the opencontainer.org website? I missed it. I only noticed it this week.
Amazon or not?
I think they were. I think they were, yes. Sorry? Anyone? No, Joint was there. Ubuntu. Whereas they are the biggest provider of Linux versions on Amazon, they weren't on the list because what does Ubuntu do? They provide LXD. Well, I won't go into LXD, but they have sort of their competitor LXD. But meanwhile, they are still completely supporting Docker. They're completely supporting whatever Docker is doing, and because they provide the most of the service anyway. So it's not that they won't support this, but they don't. We'll see what happens. So this is how far I can go regarding security for containers. Is it secure? Is it unsecure? Maybe some of you saw the sentence of Joanna, the lady who makes CubeOS. She says Windows is unsecure. You can never use inter-process protection mechanism. All those very nice inter-process mechanisms that Windows provide, you can never use them to really protect operating machines from each other without a hypervisor. Even the most lousy hypervisor is much better than what the operating system can do. So I'm not going to argue with her. I'm not going to argue with people who do say that it can be secure enough. It can be secure. It is secure containers. I just noticed that there's many opinions. So then Niels told me last couple of days ago. He said, yes, there's something else interesting going on. That's about libc and Go. So a normal application, when it makes a transition from user mode to kernel mode, it calls libc. And then libc will do some inter-process communication for going into the kernel, probably an interrupt or something, and the transistor goes into a state change. It goes from ring 3 to ring 0 on the Intel processor. But Go, the language of Go from Apple, what that does, it can do the system kernel calls itself. So it doesn't depend on libc. So there you see a little bit less entropy. Whereas before we had libc, now you can make a monolithic application. Directly, of course, it still runs in user space, and then it makes a transition to kernel only when needed. There's a really nice blog from Kelsley, where he explains how you can make a very small Go application, totaling of 6 megabytes. So that's including the scratch, very, very small Linux kernel. And then you see another lowering of the entropy. You have a very, very small Linux kernel. You have a single statically linked application, which I think has less attack vectors. I don't know whether anyone agrees with me.
I do.
You develop in Go?
Yes.
You do, okay. Well, I don't, but it seems to me this is a way to get less entry points and more simple entry points into an application and outside and out of an application. Then you have the URL. So this is one way to go. The next thing, which is also really interesting, what's going on, is Triton. Triton is the Greek god, half man, half fish. That's the name that Joyent gave to their container solution, where you have a Solaris kernel running a Linux operating system, or a Linux application, let's put it that way. And there again, we see the syscalls, and what they did. In here they have a translation table, or a translation, they call it LX. It came from Solaris, and back in the days, in 2004, 2005, I think they stopped with it, and then they picked it up only 2 years ago or last year. So now you have an application with these libraries calling into libc, the Linux libc, with the Linux system calls. And then they are translated into the Solaris system calls. And then you go into the kernel mode. So, again, from my perspective, I think here we have a small attack vector. If you are inside a Linux container, now you're trying to attack a Solaris kernel. Probably, the attacker will go to the neighbor, let's put it that way. Eventually, you can come there, because there is still a lot of entropy. And of course, if you know you run on joint, you are able, and maybe you know some issues in the Solaris kernel, you can get in there. But I think that this is another way to look at security. I'm not saying this is more secure than Linux, but at least it's an interesting twist. next? I started with the professor from Cambridge. Remember? Well, they make Mirage OS. And Mirage OS is a Unix kernel. There, you don't have system calls. Because what they do is they link directly your application with the kernel. And only that what you need. Some libraries, they use OCaml, so it has garbage collection. The two boys who gave the presentation at the CCC conference last December, they wrote a TLS implementation, 2,000 lines of OCaml, and they linked the C code from IIS. So they didn't write IIS, but the whole process of exchange of secrets back and forth, that whole process they wrote in OCaml. Anyone guess how big? I didn't put it on the slide. How big would this complete operating system, including application, be?
Few megabytes.
How big?
3 megabytes.
2 megabytes. Startup time, 20 milliseconds. So that's where the people in Cambridge are heading to. No kernel. No kernel transition. No user space. No kernel space. But a hypervisor. But also the hypervisor has limited interfaces. You don't need file services here. You only need TCP. So you only have your TCP interface here. So you can limit also your hypervisor here and have limited entropy in that. So what he even said is you could do a DNS lookup at your DNS server. Then the DNS server could look, is that server running? No, it's not running. Oh, let's start it. And before the user gets back to the answer and goes to the server is already started. I talked to the guy Hannes, but he didn't make the switch to this would be something we could use for containers and container. I don't know why, but maybe I'm wrong. Maybe he didn't get the picture. But I see some possibilities here. Then there is queues. Operating system by Joanna Rutkowska, yeah. She has a different aim. She uses a GUI. She supports a GUI. So this is more aimed at people working on a desktop computer and they want to separate their different tasks. So your bank would be one, and your personal, your work would be separated. Small attack factor, and something else she does, here you see the storage domain. If you attack the storage domain, or if your network domain is attacked, this goes down, but not your machine goes down. DOM 0 doesn't go down. So your machine stays up running, you could reboot your network stack, and you're up and running again. An example of multi-layer defense, at least how I see it. And she uses extensively the Intel instruction set for switching back and forth between the hypervisor and the applications. Anyone? What's the issue with Intel instruction set and hypervisors? Anyone? No? Well, again, I'm not a kernel writer, and I won't never be. But what I understand is that there's many instructions that if you invoke them from within an application, from within a VM, those instructions have to be emulated and sort of translated inside the virtualization layer. But that's only for Intel. It has a very complex instruction set, as you might all know, those who looked at the instruction set. Very complex. That's different with ARM. ARM is a very clean interface for hypervisors. So it's much easier to write a hypervisor for ARM. Okay, next up. Who's next up? Who's the big one coming up? There's one party missing. Microsoft. What is Microsoft up to? Microsoft wrote one core. So they refactored their complete operating system kernel. Made a really small kernel. 64-bit only. And that kernel is the basis for Windows 10, Windows Server, for the phone, and for Nano Server. Next slide will be a Nano Server. So they also figured out that, well, we designed this in 1980, what is it, 1999, 89, something like that, a long time ago. So they redesigned completely their operating system and started with clean slate and then added whatever they needed. You add this, that, that. And they support Docker. Not currently. So if you want to run a container, kernelized container, like we've just seen for Linux, won't be possible yet. Maybe after the summer. But they do something really interesting. Okay, before that, so they had two versions. The Nano Server, which is the really, really small version, and what they call born for the cloud applications. And then they have the traditional, the core, Windows Core. Maybe some of you know Windows Core. Well, where I come from, it's really normal. So it's Windows without a user interface. So you can run a SQL Server on it, you can run IIS on it, etc. You can run most of your legacy applications. But this is far, far bigger. This is like, I don't know, I forgot the numbers, but it's like maybe 10 or 5? I don't know. But it's really small, and this is much bigger. And then they did a really nice thing. You can run a container as a container, with a Docker interface, kernel mode, separation, process separation, or you can run it as a Hyper-V container. It's just a tick box. From the perspective of the developer, it's the same. And then, as they say, it's just, what does your regulator say? Are you a bank? Well, then probably you run it in a hypervisor. Because the regulators say containers are not secure enough. At least process containers. Or you're a hoster, and you want to make sure your customers are separated, you run it in a hypervisor. So we're coming to an end. Well, on top of the Nano Server, you can run some packages, some backward compatibility for 64-bit, 32-bit applications. You can run a Hyper-V host, so that means the Hyper-V machine, you install it on a physical machine, and then on top of that, you run your Hyper-V guests. You can run, really interesting, they have some file services and some other things. They call it reverse forwarders. And with one of those reverse forwards, you can run the normal stack of things we're used to. So there you see, they want to run normal Linux applications on Windows. Well, that will succeed? I don't know. I heard that Microsoft runs 75% of their services on Linux in Azure. I don't know whether that's true. That's the rumor I heard. That was Microsoft. And there's another company, big company, who feels the heat. That's Intel. So they announced Clear Linux. Linux is yet another small Linux distribution, which is really fast, and it runs 1,000 virtual machines on one host, and they can start up in 200 milliseconds. That's what they aim at. So why are they doing that? I haven't read the analysis, but my personal guess is they feel the heat from ARM. If ARM is so much secure and so much simpler interface for hypervisors, maybe Intel is afraid of ARM. There are 2 billion people running with walking around with an ARM processor in their pocket on their phone. So one day ARM will be big. So, what does Gartner say? In their Magic Quadrant, we see Amazon Web Services, Microsoft, and then the rest. VMware, Joint is somewhere here. And interestingly, they say they advise to use a bimodal strategy. So that, in my sense, this means run VMs for your current application, for your scale-up applications, for your banking applications, for the things that really need security, and then for when you want to be agile, maybe switch to containers, even for enterprises. So that's my conclusion also. I can't make it better, I can't make it worse. Somehow they will converge. Somehow we will have more containers running virtualization than we have now, and we will have less enterprises running only virtualization. Personally, I think that ARM could be something coming up. I don't know. Maybe not. It offers some benefits, much faster. Not the disadvantage of virtualization that it's slow I/O. So, that was my talk. Questions?
If you're just waiting for the mic, I have it right here. No questions?
Niels, at least you.
Oh, better.
Throw it.
Yeah, thanks for the talk. I have a question about the unikernel thing that I only learned about yesterday, which sounds really fancy. But does it mean that you have then one process running in your kernel? And because if I run in a virtual machine different applications that can do concurrent things, now we're learning a lot about how to do concurrency in one process with Go, for example, and that sort of stuff. But can you say anything? I mean, I understand you just recently studied this as well, but can you say anything about how we have to rethink, develop our processes if you link them with the kernel?
Well, I don't see any reason why you couldn't be multiple processors. Is that what you're asking?
Yeah. Should you then thus run multiple kernels because you do multiple processes, although they're really closely coupled in a sense?
No, I don't think so. I think you can just use your hypervisor as you used to, and assign 1, 2, 3, 4 cores, whatever you want to one of these, well, unikernels.
So the unikernel would then still be able to do process scheduling?
Yeah? Yeah.
Okay.
So really, it's just bringing in the parts of the kernel that you will specifically use in your application, right? Audible. Right. Okay. Yeah. So no. If I understand what you're saying and just guessing through what this would be like, they are essentially just including the functionality and behaviors of the kernel into your application and giving it direct access to the hardware. Is that right? No.
Well, then please.
Take a mic.
There's actually no multiprocessing, and every runtime, there's multiple types of unikernels right now, and every runtime has to implement their own concurrency features, which will run on one or more cores. And you mentioned that you just include parts of the kernel. Actually, you just rewrite parts of the same functionality that the kernel offers. For example, Mirage OS, they wrote their own TCP stack, their own TLS implementation, everything you have to link against. But it's not just that you can just take something from an operating system and bring it in. You have to write your own stuff. So that's why.
It's like running like in 13, right? And doing like a main loop in C and booting that, period.
Exactly. So I'm not really sure about Mirage OS, about their runtime, how they implement concurrency. They have some kind of concurrency, I think, but it's not the old school process concurrency and threads.
No, I agree with you. It's totally dependent on which version or which shim you're using. It's basically a shim, nothing more.
Exactly.
So if they offer you multi-process, they offer it. If it's not there, you need to write it yourself on top of it. That's basically it. It's very, very thin.
Yeah.
My work here is done.
Maybe I can just give some look at what Kelsey did. Yeah, here. So in this case, we had a really, really small operating system, Scratch, which didn't support. So I think it didn't support something. I don't remember what. And so we had to write a small routine to implement that because the service wasn't available from the kernel. So there you see exactly the same what you're describing.
You're killing me. Just came from that.
I think there's a difference. It's not an operating system. It's userland. The operating system is underneath in your container space, which is running on top. So this is running on top of your kernel. So it's not an OS.
I agree, but the same principle that if you have some functionality, because it's a really, really small, you use a very, very small kernel, which supports barely nothing.
So basically what CoreOS does.
I'm sorry?
What CoreOS does. CoreOS does that. They have a very small kernel and they offer you that and you can run containers on top of that. But they're providing you the vehicle to run something on top of. So what you're describing, Scratch, is not the vehicle. It's something that runs on top of the vehicle. So it's not an OS. It's userland.
Correct. No, I agree with you, but...
Well then, let's get a big round of applause for Bart, please.